So getting into the problem, so we have for this one, we have a 3-meter high, 5-meter wide wall, and it consists of this kind of smaller cross section. So they've taken this bigger wall and they've broken it up into just this small part of the wall that's representative of everything else. They say the horizontal bricks, so the bricks are K equals 0.72. They're separated by a 3-centimeter thick plaster layer and also a 2-centimeter thick plaster layer on each side. So sorry, there's also, sorry guys, okay, 3-centimeter layer plaster. So that's this 3 centimeters. And this has a K of 0.022. And then we have 3-centimeter thick rigid foam that's given. K is 0.026 on the inner side of the wall. The indoor and outdoor temperatures are 20 degrees Celsius. So we have 20 degrees Celsius in here, -10 out here. And we have the 2 convection coefficients. So on the inside of the wall, we have 10 watts per meter squared. On the outside, 25. So assuming one-dimensional heat transfer and disregarding radiation, determine the rate of the heat transfer through the wall. And so I guess I'm sure you've seen it before where you're kind of given an equivalent heat transfer of a wall. And whenever they do that, it does involve a lot of this kind of analysis where you consider all the modes of heat transfer. So there's heat transfer that's kind of coming through this middle part. You can see that this is slightly lower than the brick. So the amount of heat that can escape through there is slightly less than the brick. And so what typically they're going to do is they're going to create, actually this analysis is what they do to find the equivalent heat transfer of the whole thing. So they just consider all of the different modes and then they extrapolate that for the whole wall. And so of course the way to do this is we do our resistance network, which is just this very handy way of sorting all this out. So we call this T infinity 1. So this is the inside of our wall. And then first thing it's going to do is it's going to go through the foam. First thing it's going to do is it's going to go through this convection. And so we'll call this R1. And we know this is associated with the convection. And then it'll go through the foam layer. So if you guys did the project, you've already done this analysis pretty extensively, R2, so that's through this plaster layer. Then it's going to go, and then in this case, they say the heat transfer gets split up into 3 different ways. So it goes through here, it goes through the brick, and then it also goes through this side. And so when we do our analysis, we'll see that the way the heat transfer goes through the 2 sides will be equal. But we'll call them 2 things, right? 2 resistors right now. So we'll call this R3. Then through the brick, we'll call this R4, and we'll call through the other side of the plaster R5. And then it'll go through the plaster one more time on the other side. These 2 are the same, so R2 and R6 will be the same. And then it'll, once again, go through the outside, which we'll call R0. And actually, I'm just looking at my numbering scheme here, and I'm noticing it's not matching theirs. 3, 4, 5.
You missed the resistivity for the foam.
I did, yeah. Absolutely. So just to keep the numbering scheme consistent with the answer I have, so we'll call this actually Ri. And this will be related to the convection. Then this will be the foam. And then plaster, the 3 bricks plaster, yeah. So you get the idea. And so after that, it's actually, I guess, not a particularly difficult question. What we're trying to do, we're trying to find heat transfer through the whole wall. I'm not actually sure where it says that in the question. Or determine the rate of heat transfer through the wall. So ultimately, once we've set up all this, it's not a very difficult question. But it's important just to remember how powerful this is, I think. This is T outside.
Sorry, could you repeat what are those thermal resistance?
Yes. So Ri, so this is the convection resistance. So between the air that's all the way out here and whatever the temperature of the surface of the wall is, there's convection, and this R represents that convection. Then everything else is different modes of conduction through this wall. So it first has to pass through the foam. It then has to pass through this plaster layer. And then it goes through 3 modes of heat transfer. And again, it's really 2. We'll note that R3 and R5 will be the same. But some of the heat that's kind of passing through here will go at a different rate than the heat that's passing through the brick, and then the heat that's passing through here. And so this whole thing is the kind of brick foam combo. That whole thing. Then it goes back through the plaster. Sorry, this should be plaster. Then again, convection on the outside.
Okay, so inside the brick, is there radiation there?
No. So the brick, I mean, maybe it's a little odd to the way it's drawn as white, but this is a material. So this is the brick material.
Okay.
And then it does say disregard radiation, and so that radiation, it's talking about the radiation that would be coming from this wall.
Yeah, I saw this hollowed.
Right, yeah. So this is not hollow, it's a brick material.
Okay, thank you.
Yeah. Okay. Okay, so now it just becomes a matter of systematically going through each version or through each one of these and finding the R, and then we'll add them all up to find the equivalent thermal resistance. We'll be able to use that to very easily find the heat transfer through the wall. So we'll do this systematically. R at the inside is going to be equal to R, we'll call this convection at the inside, which is equal to 1 over HA. And of course, this 1 over HA comes from our original convection equation, which was HA T surface minus T infinity. So this equation, which we were using before, that's what they used to develop this. This we have 1 over our 10 watts per meter squared Kelvin. And then our area, which is 0.25 times 1 meter squared. Okay, and then this 1 meter squared So I think what they're doing, and this will all come together at the end if what I'm saying is right, but they're taking a cross section this way, and they're taking kind of a representative 1 meter in this direction. And that will be important when we scale this up to the actual cross section of our wall. So for now, because we've kind of only taken this representative piece here, we're going to take a representative 1 meter, and then we're going to right, so someone's saying I thought it was 5 meters. So it's 5 meters through the wall. So yeah, so it's 3 meters high, 5 meters wide. So yeah, the geometry of this is a little confusing, I find. But I think actually this direction that I've drawn the 1 meter, from what I understand, this is the right, yeah. So this is it will be 5 meters high, but we're also only taking a representative piece here. And so it's representative in this dimension, representative in this dimension, and then we're going to scale that up to this 3 meter by 5 meter, if that makes sense. Maybe at this point you could have done the 5 meters and then you could have scaled it differently, but it's also, I think, good for me to follow the answer key so that I have the right numbers. A little, I mean, not that we can't do it another way, but it's a little easier than having to recalculate it. Okay, 0.4 degrees Celsius per watt. Okay. So our R1, which is through our foam, is equal to L over Ka, which is RL 0.03. That's in meters. So then this 0.25, yeah. So in both cases, the 0.25 comes from the 22 plus the 3, the 1.5 on each end. Hopefully it's clear. This is 4.62. So you can see this is a very high resistance, especially compared to the convection. So as we go through, we can look at all the resistances. So this becomes a little bit repetitive now. So our R2 is, this will save us a bit of time. Luckily, our R2 is equal to our R6 because it's the same plaster layer on each side. This is our 0.02 thickness. All right. And then also saving us a bit of time, our R3 is equal to our R5. So as we recall, this was R3 and R5 are the two sides of the brick that are symmetrical. So those will be the same. And then that middle portion, the brick, and so you can see the plaster has a much higher thermal resistance than the brick, but that's also a property of the fact that it's much thinner as well. So if you look at the properties of the brick versus the plaster, the brick is going to allow a little bit more heat transfer than the plaster, but not to this same magnitude. So part of it is just that if you look at the actual geometry of the problem, just because there's less plaster than there is brick, there's naturally going to be less heat transfer passing through there. And so its size is also related to its thermal resistance. All right, and now we're on the last one, our outside. Okay, and so now we want to find the equivalent resistances. And so we know anytime you have something in series, the resistance of one is just the addition. This is equal to R of this whole thing. And then the other rule is with parallel. If we have R1 and R2, our R equivalent, or just our R is equal to, or sorry, 1 over R is equal to 1 over R1 plus 1 over R2. And you may have seen another version of this, which is, I think it's the addition over the product. And that would be just equal to R. And that's a little more handy because it's equal to just R. But this one is more versatile because we can keep adding on resistors with this format. And so this equation is going to be the one we're using for this because we have 3, though 2 are the same. So I don't know. You could do it with the fancier version of this, but I like this one because it's a little bit more versatile. So our R, we're going to call this mid, and what we mean by that is the kind of brick plaster cross section that had the 3 resistors. So we'll do 1 over this is going to be equal to 1 over R3 plus 1 over R4 which is 1 over. So this will be watts per degree Celsius, and then our actual R mid will just be the inverse of that, 0.97 per watt. Okay, our total for the whole wall is now this R mid, this is our equivalent resistance, and so that we'll just put that in series with everything else. So Ri plus R1 plus R2 plus R mid plus R6 plus R naught. And I'm not going to rewrite everything because we have all the numbers quite handy, but we'll take all the R's we just added up and we'll get 6.87 degrees Celsius per watt. Okay. So now we can calculate our heat transfer through our what we're calling our representative sample of the wall. So we're saying our steady state heat transfer, the representative this is Q dot is equal to T infinity 1, so our inside and our outside over our equivalent, our total. So the top here we have 20 minus 10. Our total was 6 point. This is all in degrees Celsius. And once again, I actually don't particularly like the way they're doing their units here. I prefer to call this a delta degree Celsius. I think it's clear, a little clear. And just to expand on that a bit, so the increment of 1 degree Celsius, so a delta degree Celsius is equal to the increment of 1 degree Kelvin. But something in degrees Celsius does not necessarily equal something in degrees Kelvin, or it doesn't equal that. And so anytime you're questioning whether or not to use degrees Celsius, it really is a matter of if you're talking about a difference of temperature or if you're talking about an absolute temperature. So in radiation, we deal a little bit more with absolute temperatures. We will have a temperature raised to the 4 before we subtract it. In that case, you have to convert to Kelvin. And you'll see other cases where you don't necessarily have a difference of temperature explicitly like this, but the equation will include taking one temperature, then multiplying, and then adding it to another temperature. Yeah, so someone just asked if we take the cross-section account, and yes, there's one more step to this question, and we will do that. It's a good point. I can stop my ramble, but if you have more questions about that, or you can ask me. But just something to keep in mind that, yeah, I guess degrees are one of the weirder units. I always like to push it home because I messed that up on one of my first co-op jobs and ended up oversizing something. Luckily, we caught it before anything was built, but it's a nice thing to go into the workforce knowing, I guess. Okay. So the total area, is that 3 meters times the 5 meters, which is 15 meters. All right, let's see what they're doing here. Okay, so that's quite a sidetrack. Okay, so we're back to the question. I never gave you the answer for this. So once we find this, we can find our 4.37 watts. Okay, and of course, this 4.37 watts we found was this kind of representation of a cross section. And so what we actually wanted is we wanted in watts per meter squared. And so to find that, we say our small q, or q per area, is equal to our 4.37 watts divided by our 0.25 meters squared, which gives us 17.5 watts per meter squared. And so this is kind of our more useful number. Then, since we have our total area, 15 meters, we can find our Q dot. And this is equal to 263 watts. And so, of course, if you had taken that different cross-section, if you had decided to use the entire cross-sectional length or width of the wall, you would get a different number here, but then you would still end up with this same number here before you added it. And so you would end up with the same answer. Okay. So that's this whole question, the whole